What's up, everybody? Yo. All right, so let's see. Yesterday we looked at two inverse functions, the exponential function and the logarithm function, and we computed their derivatives. Today we want to do the same thing, only with trigonometric functions. Of course, we have an advantage. We've already computed the derivatives of trigonometric functions. So all that's left are the inverse trig functions. Now, it's possible you don't remember what these are so well, so we'll talk about those a little bit. I also want to give you a more general formula, which is whenever you start with a function and you want to know the derivative of its inverse, I want to give you a little formula for how to do that. All right, so let's start. Differentiating inverse trig functions. All right, so remember that if you have a function, right, it takes some real numbers and it spits out other real numbers. Right? And sometimes that function is a one-to-one function, right? Which means you can't have two arrows going to the same point. And sometimes it's an onto function, meaning every point in the range has an arrow going to it. And in that nice case where the function is both one-to-one and onto, we call it a bijection. And once you have a bijection, then you know that you have a map which goes backwards, takes any point and just follows the reverse arrow. Right? We know there is an arrow going to it because the function was onto, and we know that it only comes from one point. Right? There's only one arrow which came to it. So I just go along the arrow backwards. And that gives me a function going the other way, which is also a bijection, and it's called the inverse function. Right? And the advantage of having inverse functions, you know, if I start on one side, apply the function, then apply the inverse function, I have to end up back where I started. So, just very quickly write these properties of inverse functions. So if f is a bijection, then there is an inverse function which we write f to the minus 1. This is an abusive notation because normally if I write something to the minus 1, I really mean 1 over it. If I write x to the minus 1, I mean 1 over x. This does not mean 1 over f. Okay, so this is confusing notation, but it's standard notation. I'm not going to change it. Okay, fine. If I compose a function with its inverse, then, well, this is what I said, right? You follow an arrow one way and then go back the other way, you get back where you started. Okay? And the same thing holds if I reverse the direction. If I apply f, and then f inverse, I get back where I started. So the example we have already is we have the function f of x equals, well, say, a to the x. A greater than 0. And the inverse function is log base a of x. And it's just by definition. And that's how you define the logarithm, as the inverse of this function. And so, of course, these two formulas turn into a to the log a of x equals x, and log base a of a to the x equals x. graphically, there's a graph of a to the x. And here's a graph of log base a of x. And if you want to obtain one graph from the other, well, you draw on the line y equals x. Right? And you turn it into a mirror. And you just reflect this across the mirror. And so the reflection of a to the x across the line y equals x is the log base a of x. And the reason why that is when you have an inverse function, it's basically just saying you're swapping the x and y value, right? If I have f of x, okay, I plug in x and it spits out y. F inverse takes y and spits out x. So it just swaps all the coordinates. So every point on here, right, if I have a coordinate x comma y, that has to get flipped to y comma x. Okay, so this point reflects across the line. Okay. Now the key, of course, here is I had to start with a bijection. Let's look at sine of x. Okay, this is going between 1 and minus 1. Pi over 2, pi, 3 pi over 2, 2 pi, minus pi over 2, minus pi, minus 3 pi over 2, minus 2 pi. Okay. So this is roughly what the graph of sine of x is. Is it a bijection? No, why not? The horizontal line test. What does that say? Well, it fails for so many reasons. One, if I start passing a line through here, what happens? Well, I hit the graph multiple times. Okay? That is the same points. For instance, minus pi and 0, right? They all give me the same y value. Okay, so I have multiple arrows going to the same point. So it's definitely not one-to-one. Is it onto? Well, that's not a fair question. I didn't tell you onto what. Say onto the real numbers. Does every real number show up as a y value? No, certainly not, right? Okay, but we always have this really nice trick for making something onto. Just restrict your range to the actual range of the function. So sine of x is a function from the real numbers to the interval minus 1 to 1. It does get everything in between minus 1 and 1. And it is an onto function on that interval, but not, I mean, on all the real numbers, but not 1 to 1. Okay, this kind of puts a crimp in our plans, right? Because we wanted to talk about inverse trig functions. Right? And inverse functions only exist when you have a function which is both 1 to 1 and onto. We have onto, but we don't have 1 to 1. How do we solve this problem? Well, we cheat. Right? That's what you do in math. When you can't do something, you just pretend you could. Okay, now how could we? Well, we have to make the function 1 to 1. How do we make this function 1 to 1? Well, we just restrict the domain. Okay? We just make the domain small enough that it is 1 to 1. Now, there's a lot of different ways to do that. Right? The most typical way to do it is to restrict your domain between minus pi over 2 and pi over 2. Okay? If you do that, you're just going to get this bit of the graph. Just from here to here. Now, if you just look on that bit of the graph, is it 1 to 1?
Mm-hmm.
Sure, right? Take horizontal lines. I'm not duplicating anything. I'm just going up from -1 all the way up to 1. No duplication. It's still on 2. And I've somehow hit, I've hit everything I need to hit. Okay, everything in the graph, every point in the graph is fine. And if I go a little bit more, it's going to turn around and it won't be 1 to 1. If I go a little bit more this way, it's going to turn around and it won't be 1 to 1. So this is somehow the best I can do. So this function is not a bijection. But the function sine of x from -pi/2 to pi/2 is now a bijection. And so it has an inverse. So there exists an inverse. And the way the inverse is going to work is, well, you give it some y value, and it just goes over to the graph and says, okay, what's the x value? Okay, that's my output. All right, so if you tell it 1, that should be a teeny bit lower. If you tell it 1, it's going to go over here and say, oh, that came from pi/2. So the inverse function is going to take 1 and send it to pi/2. So we have an inverse function, which is called this, or sometimes Arcsine. And since our original function went from this interval to this interval, the inverse has to go backwards. So it goes from -1 to 1 to the interval -pi/2 to pi/2. And if we want to graph this, well, in our head we can, first, okay, we know it's going to eat things between -1 and 1, and the output is going to be between pi/2 and -pi/2. Okay, this is definitely not to scale. And you can see what's happening, okay? Things like -1 gets mapped to -pi/2. So -1 should be down here. Okay, and 0 gets mapped to 0. Right, and 1 is mapped with pi/2. So it looks almost the same. And actually, that shouldn't surprise you. If we draw the line y equals x in here, let's see, I guess that should be hitting, that's a little bigger, so that's the problem with not drawing to scale. Pi/2 is about, what, 1.5, a little bigger than 1.5? No, 1.5, no, 1.57, say. Okay, so it should actually, that was 2, then there's 1.57. That should actually be the point where, okay, so it somehow has to reflect across this, but you see it's not going to be doing a whole lot of reflecting. I mean, it's not missing by much. This almost looks like y equals x at certain points in here, I mean, especially around 0. It really looks like y equals x. So it just gets flipped around a little bit, and so instead of curling up on the ends, it should be going the other way. Something like that. Incidentally, as an aside, why does this function y equals x, right, almost look like it's the same thing as sine of x around 0? I mean, why does sine of x almost look like this line, y equals x, around there? Well, remember we proved last time that, or maybe the time before, no, it's whenever we did the trig function, right? That the limit as h goes to 0 of sine of h over h was 1. Right? That was this limit we used to compute the derivative of sine. Well, this says that when h is small, right, as you get close to 0, sine of h and h get very, very close to each other. Right? Which means that, well, that's just the line, if you like, y equals x, and there's sine of x. They get really, really close around 0. Which means if I asked you, what's sine of 0.12? It wouldn't be a bad guess to say 0.12. Because these functions are actually pretty close, right? If you divide them, you get 1 as h gets closer to 0, which means that they're almost the same function around 0. So this gives you a very easy way to compute sine when it's close to 0. You just forget that it's sine. So what's sine of 0.002? 0.002, right? Okay, so this is very nice. Okay. Later on, when we do Taylor's series, we're going to see another explanation for this. Okay, so here we have the arcsine function. Okay, so it's a nice legitimate function. Granted, it's only defined between -1 and 1. But, you know, that's something, right? And, well, if you forget about the rest of the real numbers, you just say, okay, -1 to 1. This looks like a perfectly legitimate differentiable function, right? There's no absolute value marks going on here, no little cusps, no jagged edges, nothing bad, okay? So we should be able to take a derivative of this. Okay, so let's try it. All right, so we have a function, y equals, so despite the fact that I will write it this way, I will typically pronounce it this way. That is, I'm going to say arcsine. Okay, but it just means the inverse sine function. Okay, so ideas. How could I attack this? How can I get a derivative? Well, we don't know what the derivative is, okay, for sine. But we do know what the derivative is, I mean for arcsine, but we do know what it is for sine. Okay? So how might I get sine back into the game? What's that? I mean, I don't know a derivative yet, right? All I know is that arcsine is the inverse function for sine. So for instance, I have that sine of arcsine of x is equal to x. And that arcsine of sine of x is equal to x. At least for the appropriate x's. So for instance, I can't put x's in here outside of this interval. Okay, fine. But at least I have these formulas. So how can I somehow get rid of this arcsine?
Both sides outside.
Just sine of both sides. Right? This is actually, I mean, this is the same game that we played with logarithms, right? We had something we didn't want, so we started taking a logarithm of both sides and we start manipulating. Okay, but here the manipulation is going to be nice and easy. Okay, sine of arcsine is x. And we get sine of y is equal to x. Well, now there's no more arcsine. I can start taking derivatives, and I know all the functions around. What's going to be the derivative of the left side here? Derivative of sine of a function is cosine of that function
dy dx.
Times dy dx, right? I always used to use the chain rule because y itself is a function. Okay, and this is going to equal the derivative of x. This is 1. Okay, I want dy dx. That's what in the end I want. I want the derivative, so I divide. And I get 1 over cosine of y. Okay, but I don't want cosine of y. I want x's. All right, so I get cosine of arcsine of x. Ooh. Ooh. That doesn't look nice at all. There's a way to fiddle with this thing. Now, let me show you this trick. We're going to use the trick quite often, and it's a neat little trick. So it's worth paying attention. Let's go back to right triangles. Those are so nice, yeah? Right triangle, have a little angle theta. All right. Now, when I write some expression like arcsine of x, what am I saying? Well, arcsine was the inverse function to sine. What did sine do? Sine took an angle theta, and it told you the quotient, all right, of the opposite side divided by the hypotenuse. Yeah? Okay, so what does arcsine do? Well, arcsine takes a number, which represents the opposite divided by the hypotenuse, and tells you what the angle is. Right? That's what it's trying to do. I mean, it's even nicer. If we're just talking about right angles there, I mean, it's very clear. I mean, right angles have an angle between 0 and 90 degrees, right? Okay, good. It's in this interval between 0 and pi over 2. Okay, so if I say arcsine of x, I'm saying what angle do I have to put in here to get out the sine being x? Okay, well, if the sine is x, that means the opposite over the hypotenuse is x. How can I do that really easily? Well, one way is to make the opposite x and the hypotenuse 1. Okay, so if I do this, the sine of that angle will be x over 1, which is x. Right? And so the arcsine of x will be theta. Okay? Okay, fine. That's the setup. Now, what's the length of this other side here? 1 minus x squared. Anything else, or is that right?
Square root.
Yeah, square root. We know that, of course, if you have a right triangle, side lengths a and b, and hypotenuse c, a squared plus b squared equals c squared. So, if you want to know, if you have one of these and you have the hypotenuse, then b, for instance, will be the square root of c squared minus a squared. So here, okay, you know the c and you know the x, so you do the square root of 1 squared minus x squared. Okay, fine. The arcsine of x is this angle theta. What's the cosine of theta? The adjacent over the hypotenuse, square root of 1 minus x squared. Which means cosine of arcsine of x is square root of 1 minus x squared. Yeah, that's kind of neat. Okay, we'll do it again. Okay, when we do cosine, and then so we'll get more practice on this again, because it takes maybe a couple times to get used to it. Okay. In any case, this gives us a formula. The derivative of arcsine of x is 1 over the square root of 1 minus x squared. Now, on one hand, this is rather surprising. very similar to how it was surprising when the derivative of natural log became 1 over x, right? When you took a derivative of a trig function, like sine, you got cosine, you got another trig function. So again, you would think, well, geez, if you took the derivative of some inverse trig function, you'd get out maybe some inverse trig function, right? But you actually end up with something which doesn't, at least at first glance, seem to have anything to do with sine or cosine at all. Now, you might think, well, geez, you know, this square root of 1 minus x squared, that looks really familiar to me.
Circle.
Yeah, it looks like, right, if you were going to graph a circle with radius 1 centered at 0. Okay, now there's a little problem here. This is 1 divided by that. But, okay, what's a fraction? Denominator, whatever, right? No big deal. Okay, so, but you see, oh, there must be some connection. And of course, we have this nice unit circle, right? Which is telling us, oh, there really should be some connection between circles and sines and cosines. So maybe it's not so surprising that this is, if it had to leave the world of inverse trigs, that it shows up in something like this. Okay, but right now we don't answer this question fully. We just notice there's a coincidence. Okay, so, but nicely we have a formula. Okay. Erase that there. All right, now we want to do the same game, but we want to do it with cosine. Okay. Oh, so it's probably just easier to erase. All right, so everything should go much faster now because we know how the game is played. We look at cosine as a function from the real numbers, minus 1 to 1. This time it's going to start up at 1. We're going to head down and up. And we're going to head down and up. All right, it goes down to minus 1. It hits here at pi over 2. This is 3 pi over 2. Hits 0 down to 2 pi. Minus pi over 2, minus pi, minus 3 pi over 2. Okay, something looks off. No, we missed the point. Good, good, good. All right, so we have this cosine. Again, if we restrict the range to just being between minus 1 and 1, it's an on-to function, right? And again, if we allow the domain to be as all real numbers, it's not 1 to 1. So we, of course, don't want to consider it on all real numbers, right? We want to restrict it so that we're only seeing some nice part that just gives me all the range, but I don't get any duplicates. Okay, so if I use the same one as before, minus pi over 2 to pi over 2, I get this thing. Of course, that's not going to be 1 to 1. So here I'm going to switch and go from 0 to pi. Just hit this symbol. And if I do this, I'm going to get all of the values between minus 1 and 1, and I don't get any duplicates. So this will be a bijection. Okay. The inverse function we call arc cosine. instead of being a function from minus 1, 1 to pi, minus pi over 2, pi over 2, it goes from minus 1, 1 to 0, pi. And then all these formulas with sine turn into cosines. Okay, now this picture's wrong. So since the range is going to be between 0 and pi, you know it's not going to go down here below 0. So let's see, a few things. When you plug in 0, you're supposed to get out 1. So now if you plug in 1, it's going to spit out 0. If you plug in pi over 2, you get out 0. So if you plug in 0, you should get out pi over 2. Now this thing should go all the way to pi. So put a pi up here, pi over 2 here. There, and then if you plug in pi, you're supposed to get out minus 1, so if you swap it minus 1, it's going to give you pi. And if we draw this in here, okay, well you can see what it's kind of flipping across. So you have to look. Going the other way. Let's see, if you flip that across, how does that look when you flip it across? How should it buckle? Should it buckle the other way? Let's see how it should buckle. So it could look like I just drew it, or it could look like what do you think?
It's that way.
You think it's this way?
Yeah.
Like that? Or come all the way down? Like that. What do you think? You need to be able to flip this in your mind, right? Okay, it's exactly this sort of question which is going to motivate the second half of this class. Okay. Those of you who've seen this before know that there's a way of actually answering this question. We're going to have to use the first and second derivatives to graph things like this, and in particular the second derivative, to decide what shape this graph is going to be. So for now, I leave it to you to reflect this graph and try to figure out what it should look like, just based on reflecting it. Okay, and then later on, we'll be more careful and see what it's really going on. Okay. But for now, we don't need the graph, because we're just going to try to compute the derivative. All right, so if I start with the arc cosine, what game should I play? Well, same one I played before, right? Just take the cosine of both sides. Right. Okay, take a derivative. What's the derivative of cosine of y? Negative sign, very good. Y times dy dx, right? Y is a function of x, you have to use the chain rule. Okay, and this equals, well, the other side is derivative of x, which is 1. Okay, we divide by minus sine of y. Of course, I don't really want to put y in here. I want to put arc cosine. Okay, so I'm back into the same ugly situation where I can use my right triangle. Okay, the way we attack this, we start on the inside. So we're looking for the arc cosine of x. Okay, so we want to make theta this arc cosine, but if that's the case, then we mean that cosine of theta should be x. Okay, to make the cosine of this angle x, we can make the adjacent side x and the hypotenuse 1. Okay? Well, then that tells me that this other side, using this exact same formula, is square root of 1 minus x squared. And now the sine of this angle, right, because theta was supposed to be the arc cosine of x, the sine of this angle is the opposite of the hypotenuse, right, which is, again, square root of 1 minus x squared. So it almost looks the same, except, I have a minus. That's the difference. So this is really neat. The derivative of sine is cosine. The derivative of arcsine is 1 over root 1 minus x squared, and the derivative of arc cosine, right, is negative 1 over root 1 minus x squared. Right? Just like the derivative of cosine is negative sine. So somehow adding c's always gives you these minuses. Just like when we did derivatives, right, of all the trig functions. And as soon as you started adding a c to any of the functions, you got the same thing out, only with a minus sign. Maybe you had to add some c's somewhere. So we'll record this. The derivative of arc cosine is minus 1 over the square root of 1 minus x squared. Cool. Time goes fast. All right, let's quickly see what's happening for tangent. All right, so remember, tangent repeats itself in little windows that look like this. So it's going to do the same thing over here and over here. Okay? So this one is clearly onto all the real numbers. Right? It hits everything up, it hits everything down. So we don't have to restrict the range at all. As for the domain, well, of course, if you do horizontal lines, you get into trouble. You won't get a one-to-one function. But it's pretty clear how you should restrict it, right? Just go between minus pi over 2 and pi over 2. So we restrict the tangent function to the domain minus pi over 2, pi over 2. And it will be a function which is onto the real numbers. So there is an inverse function. And of course we call it arctan. And it goes from, well, actually, it's a set of all real numbers, so you can stick anything in it you like, and it spits out some values between minus pi over 2 and pi over 2. And it has all the inverse properties you expect. Okay, fine. Let's not worry about the graph for now. Let's worry about the derivative. Okay, you just keep playing the same game. Take the tangent to both sides. Got rid of the arc tangent, take a derivative. Now, Who remembers the derivative of tangent? Secant squared. Very good. Okay, so we get secant squared y times dy dx equals 1. We divide. And dy dx equals 1 over secant squared of y. Of course, I don't want y, I want arctan. Okay, I go back to my right triangle to figure out what this is. Okay, I'm looking now. I want theta to be the arctangent of x. Okay, so theta is the arctangent of x. That means that the tangent of theta should be x. Okay, so tangent is opposite over adjacent. So if I want the opposite over the adjacent to be x, then I make that an x and that a 1. Okay, now the Pythagorean theorem tells me that this is the square root of 1 plus x squared. Fine? And now I'm supposed to take the secant, and whatever that is, I'm supposed to square it. So what's the secant of theta? Well, let's see, secant is 1 over, is it 1 over sine or 1 over cosine?
Cosine.
Okay, it's cosine, right? With these, it always is switching up. Secant goes with cosine, cosecant goes with sine. Okay, fine. So 1 over cosine. Now, cosine is adjacent over hypotenuse. So 1 over cosine is hypotenuse over adjacent. So hypotenuse over adjacent. Okay, so it's just 1 plus x squared, square rooted. And then I'm supposed to square it. Ah, cool, it gets rid of the square root. So I end up with 1 over 1 plus x squared. So the derivative of arctangent is 1 over 1 plus x squared. Okay, now we don't have time to really go into the other three, secant, cosecant, and cotangent. But I should point out to you that it's a little weirder with them. And so you have to be more careful when it comes to defining these things. For instance, with secant and cosecant, cotangent isn't a problem, but secant and cosecant are not going to be defined on one continuous interval. So next time there'll be a quiz. But the next time we talk, mention that, let's see, how does that work? I think it's secant. You kind of have to look at the picture and then you can see what it should be. I think you define it from 0 to pi over 2 union pi to 3 pi over 2. Well, whatever the range is. So you actually break it up over 2 different intervals that are disjoint. And you do that because it's going to make the derivative better. If you define it over some continuous interval, then it's harder to write down the derivative. Okay, we'll talk about these things next time. Whatever this secant is, though, you can try to play the same game. All right, once you decide what the correct inverse is. All right, and if you start playing, then of course you need to take a derivative, and you'll get secant y tangent of y times dy dx equals 1, and then you'll get dy dx equals 1 over secant of inverse secant times tangent of arc secant. And, well, this, for instance, is a place where it might be nice to know that you're choosing things appropriately so that everything's coming out in the right domain, or the right range. In any case, that just becomes x. Right? And then I leave it to you as a little exercise to use one of these triangles to compute, well, it's not there anymore, tangent of inverse of arc secant. Okay, and it's not so hard. Yeah.
There's a quiz next class.
There is a quiz next class.
On derivatives.
Yeah, on derivatives. Yeah. By the way, I put up, I don't know, a day or two ago that there would be a quiz on the website. I will usually write that on the website before I say it in class. So it really behooves you to go to the website every day and just look at the, class updates.
Is inverse included in that?
I don't remember.
Okay.
I wrote it so long ago.
So you have to memorize like all the derivatives.
Yeah,
Okay.
all the derivatives.
Well, no.